Welcome back to a new episode of Passion for Technology, the podcast from EBV Elektronik. Great to have you with us.
Welcome to the Passion for Technology podcast. Climate protection is shaping up to become the most important task of our generation. It requires the reduction of hazardous gases and air pollutants, carbon dioxide above all. In Germany, 85% of greenhouse gas emissions are energy-related. Energy efficiency is paramount to achieving the overall goal of a more sustainable future. Machines, vehicles, and buildings need to use energy in a more efficient manner, requiring intelligent solutions. Semiconductors based on wide bandgap materials are among the most hotly discussed topics when it comes to increasing energy efficiency. In this podcast, initiated by EBV Elektronik, the leading European semiconductor distributor, we want to take a closer look at wide bandgap materials such as silicon carbide and gallium nitride and see what possibilities they offer. I'm your host, Mustafa Isik, and I'm happy to welcome two distinguished guests to our podcast. Lisa Dietrich joins us from Broadcom, where she's a senior industrial field application engineer. Hi, Lisa.
Hello there, Mustafa.
Karl Lehnhoff works for EBV Elektronik as director for the industrial segment. Hi, Karl.
Hi, Mustafa.
Everybody is talking about SiC and GaN. Lisa, what's that all about?
Yeah, SiC and GaN are materials that are used in power electronics. Maybe some, easiest way to imagine that is that we need power electronics in many inverter and converter applications that are used in motor drive systems, that are used in renewable energies, like, for example, photovoltaic, that are used in energy saving systems. It's all about converting voltages or currents from one level to the next level to actually be used in different system configurations.
Karl, could you explain to us what wide bandgap semiconductors are?
Yes, for sure. So let's go one step back. So today we use silicon-based transistors like MOSFETs and IGBTs. And wide bandgap, they should replace these standard transistors for the future. And as the name already mentioned, they have a wider band gap. And the difference here is really that the band gap for standard silicon is in the range of 1 to 1.5 electron volt. And for wide band gap is 2 to 4 electron volt. And wide band gap offers much higher temperature. So this is in the range up to 300 degrees Celsius comparing to 170 to 180 degrees Celsius, enables faster switching and also higher frequencies. It has higher breakdown fields with shorter channels, which offers lower resistance on resistance. And this ends up all in lower losses. And also, I think it ends up in higher efficiency, which you can generate with these devices. And also you can reduce size and weight. I think these are the three main advantages which you can reach out with this technology.
With all the discussion about SiC and GaN as wide bandgap materials, how far along is this technology today? What are your thoughts on this?
Let me even go back a little bit a step. Together with Broadcom, the Technical University of Cologne, we start already in 2013 on a white paper on a motor integrated inverter, which was based on silicon carbide. So silicon carbide is one of the wide bandgap material which is used. The advantage was really to get rid of the heatsink, to integrate everything inside the motor, not have it outside as a box beside. When we look on that today, in many servo drives, this is becoming a standard. I would say not in every application it's a standard of today, but in a lot of already. And the advantage here is really that on system cost base, you are equal, but on life cycles cost, you're already much cheaper than a conventional solution. And this makes a change for me.
Right. And Karl, I would agree with you. I mean, the activity, this is really, let's say, using silicon carbide and GaN material. The idea has been around for more than 10 years. But just at the beginning phases, the different manufacturers were not really aligned with their specifications. And it was quite difficult, even, from our side, from Broadcom side, from the driver of these power electronics, to actually produce a product that would cover all cases. And in the meantime, the technologies have become more consolidated and aligned specifications and are even in the position to replace the former technology being used, the IGBTs or the MOSFETs, in a kind of a one-to-one pin configuration. So the developments are moving in the direction to replace existing technologies, and it has become easier to do so in terms of the driving technology being used and also in terms of cost and requirements for the system.
Karl, how do the materials differ? What does that imply for their potential use cases?
Between the both material we have, they have differences in the structure. So for silicon carbide, there is typically used vertical planar or trench technology. This offers higher voltage and higher power. That means really for highest power application is good alternative to existing solutions which are covered with IGBTs today. And here there will be the change. When we look to gallium nitride, they have lateral devices and different suppliers are using different technologies. Gallium nitride compared to silicon carbide offers much higher frequency. So even with silicon carbide, you can get higher frequencies compared to standard devices, but using gallium nitride, it's much higher frequency. So this offers the highest power density which you can reach. The difference here is a little bit also that it is only used in the moment up to 650 volt. So with this, it is not the highest power application, but it's with a higher density in the power. And this could be any application like any chargers, whatever, should be really built small. And it's also good in Class D audio inverter. So if you are a high fidelity fan, it's a good choice to look for an audio Class D audio device which use GaN inside.
So if I could add something there, exactly these different kind of materials, as mentioned from Karl, in the higher frequency, it also requires them to be driven differently. So, as I mentioned before, the gate drivers, that's the product that we deliver to actually drive the power electronics. They need to have those higher switching capabilities. They need to have higher output currents, for example, because by driving or providing a higher output current, you're able to quickly charge the silicon carbide and GaN device, and you can therefore improve the overall system efficiency. Other things have to do with the protection of the device. There's something called under voltage lockout because you don't want a power electronic device to turn on or off when it shouldn't. So there are certain features there that you have to take care of from the driving side, which is different due to the different materials being used.
Lisa, what would you consider to be general advantages and disadvantages of semiconductors with a silicon carbide or GaN base?
So the advantage is very clear are the higher frequencies. There's faster switching transition times, which means lower switching losses at the end of the day. This higher efficiency allows for a much smaller size and smaller weight for the application. Karl mentioned it at the beginning that we have something called this lower on resistance. You can use smaller components. You don't need as much cooling on the power electronic devices. So that all means at the end of the day, you have less weight within your system in a much smaller size. As Karl mentioned from the white paper that we did in 2013, the fact there was that we could integrate a system into a motor itself, right? And we didn't need an extra box with extra cooling and a much larger design. There are some disadvantages, if you want to call it that. The higher switching speeds means there's much higher slew rate, or something called DVDT, which is the noise of switching within the system. And in that case, you need to have a driver with a high noise immunity. Because as I said before, you don't want a power electronic device to be turned on by accident, right? That you would cause something called a shoot through, which would damage the system. So our optically isolated gate drivers are inherently immune to noise, but also through the newest technology that we use can withstand much higher DVDT, up to even 100 kilovolts per microsecond. And the ability within our driver system to actually protect the power electronic devices and have these requirements when you have that high switching, high throughput, you also have to quickly protect the device, be able to have some kind of a fault feedback. And you may call that a disadvantage in terms of having to reach these high frequencies, actually have that quick response, or you may call it an advantage if you have a driver that can do that.
Karl, where do you see the greatest potential for using SiC and GaN?
So the greatest potential is really in all power-hungry application. So everything which needs power. And I think a good example is if you have a drive application in an industrial drive or other drives. Here we know that when you operate them over the lifetime of 20 years, that 99% of the life cycle costs comes from operation and maintenance. So only 1% comes from the production of the drive itself. So if you increase the efficiency by 1%, the 1% increase you get back over 20 years, and it's nearly 1% of the total life cycle cost. And this is the biggest potential. And all power hungry or energy hungry application there fits perfectly for that. It could be the e-vehicle, it could be a drive, it could be a train, it could be whatever. At the end, you can go down to say every application. And a good example is this year changed the energy labeling in the white goods. So the A+++ is now A. So the A is now, I think, G. To reach now an A, you have to bring in the highest efficiency devices. You can't use standard devices anymore. It has to be changed because everybody would like to buy a device for his household with the energy labeling A. Nobody will buy one with G. And I think this is the change. And here it is a big advantage to use wideband gap devices.
Applications make something as new as this very tangible. So could you please elaborate a little more on, let's say, with one or two examples of applications that further demonstrate the potential of SiC and GaN components? Lisa.
Right. So as Karl mentioned, anything that is, let's say, hungry for efficiency would be a very good example for something to use silicon carbide as a power electronic. So one thing that you see in our daily lives are these photovoltaic panels on the house, right? On everybody's house or if you go through the countryside, you see all these photovoltaic farms. And there, if you can increase the power conversion efficiency by using silicon carbide, then you have a big advantage in terms of the energy we all need on a daily basis, and also in terms of money savings, right? Which is what makes the world go round, I guess. The second thing has to do with chargers. So, we all know from our mobile phone, that's what we have to constantly charge. And now more and more our vehicles. And fast charging requires high frequency switching. So any kind of battery chargers, electrical vehicles, that's where you can really get a big advantage of using wideband gap components.
Karl, would you consider the use of SiC and GaN semiconductors to be profitable today, let's say in terms of energy saved?
Clear yes, out of my view. To give you an example, if you look in e-vehicles already use wideband gap devices inside. When you higher the efficiency by 1%, this ends up for you in a longer range of more than 1%. And it's not only the losses of the inverter itself, also you have less weight and you need less pumping power for the cooling because you have less losses. And the other point is if you brake, the efficiency for your braking is higher, so your recuperation is higher and you bring back your energy into the battery system. I think this is a good advantage here. You can see, and there's another one I would share with you. It's in the photovoltaic. So Lisa mentioned photovoltaic before. There's a new technology which is called hybrid active neutral point connected inverter. And this is based on wideband gap, silicon carbide in this case. And this offers a higher power density. And the factor here is 1.8 power density. That means 1.8 kilowatt per kilogram. And to give you an example, there are devices on the market, as example, the SMA inverter manufacturer. They have a standard device in the same case with 75 kilowatt output power. It has 77 kilogram weight. And they have the new one with the new technology. And it offers 150 kilowatt instead of 75 kilowatt. And the weight is 85 kilograms. So it's 10% more weight for doubling the output power.
How do you think that the cost of SiC and GaN semiconductors or electronics based on them will change over time, Lisa?
Okay, I think in general, certainly the cost of silicon carbide and GaN semiconductors will come down over time. Basically, the component price will go down as the production itself improves, as higher quantities are being produced. And in general, there are newer technologies being used, like splitting a wafer so that you're able to get more quantities out of a single wafer. But I think it's clear that silicon carbide, the actual cost of, let's say, the semiconductor chip itself, will never be the same price as a silicon device. Based on the material being used, it probably won't get down that low, but it doesn't have to, right? As Karl mentioned, if you look at the overall efficiency of the system and the cost that you can save on the system level, it doesn't necessarily have to reach the same price. Another thing is that, not all current silicon, let's say IGBT systems, will actually be replaced by silicon carbide. If it is a voltage level that doesn't need the technology or an application, then that, former or existing technology will continue to coexist with silicon carbide itself. On the GaN side, picture there may be even clearer because we have that big advantage through the much smaller size of the package, so 2 to 3 times smaller size. And that will most likely replace the silicon MOSFET technology over time, at least in the area of about the 600 volt area that I believe we mentioned before during this cast. So it really will depend. I think overall, if you ask, it will come down. Certainly the price and the cost will come down over time. And the question of whether it will reach the levels of some of the other coexisting technologies, that we'll need to see.
The use of SiC and GaN is still in its infancy. How important will it become in the future? Lisa, what part will these materials play in the enormous challenge of tackling global climate change?
Yeah, it's very interesting that you say, or that we think that it's still in its infancy. I think from our side, we can almost say it's moving towards its terrible twos or maybe even the kindergarten years, because basically we've been designing our, for example, gate drive optocouplers into the solar energy inverters and energy storage systems and power supplies over the past few years. And even today, we're saying probably over 70% of the requests we deal with from customers really are already for silicon carbide and GaN projects. So that's something that's very much active today. And we even already have multiple reference designs with different power electronic manufacturers to offer, our current portfolio with very new silicon carbide and GaN devices.
An important thing is really here we have a lot of CO2 directives in place in many areas. You only can fulfill a lot of these activities only if you use wide band gap. So we mentioned a lot of examples before. A good example, and everybody knows it, is e-vehicles. I think we see both sides. So you only can reach it when you use its technology, if you change this technology. So both areas need that wide band gap, like the CO2 emission reduction. And I think this is something which helps us in the moment. And we have had some early adapters like photovoltaics. They are already since a couple of years using silicon carbide. They are fully aware of that. E-vehicle is not thinkable without silicon carbide and GaN. And there will be other applications where we will use it, like trains and whatever. We talk about all the trucks in future. Let's see what will happen there. And even when they will use hydrogen instead of battery, they have a need to use silicon carbide or even gallium nitride, depends on the system inside the truck. And it will come, it will take some time.
Lisa, Karl, thank you for introducing us to the field and potential of wide bandgap semiconductor use in electronics. I'd love to know when and how you developed your individual passion for technology. Please feel free to share your individual origin stories with us. Lisa, how about you start? And Karl, I'd also love to know your very personal origin story.
So that's difficult to say, actually, from my side. I think that my interest and passion for technology comes from trying to answer my own questions. So it comes from working with people over the years and doing technical support. And it has developed into wanting to know how things operate or wanting to know the answer to the questions that I can't answer myself. So I have to go and find them out and find an answer and be able to share that with people around me, I guess.
So my passion comes really to work on solutions 4 or 5 years before they came to a kind of a mass market, before people are being aware of that, working on that and seeing how this will improve and come to market and change something in the world, especially when we think in the direction of wide band gap again, to do something really to reduce CO2 emission for the future, to help to make wide band gap successful in nearly every application.
Dear listeners, if you want to know more about SiC and GaN, visit ebv.com/GaN-SiC. That's ebv.com/GAN-SiC. Please feel free to subscribe to our podcast, Passion for Technology, on either Spotify, Apple Podcasts, or any of the other popular podcasting platforms. Lisa, Karl, thank you very much for the insights that you've shared with us today.
Thank you.
Thank you.